You're about to have surgery. The anesthesiologist places a mask over your face. You breathe in a gas, sevoflurane perhaps. Colorless, sweet-smelling. Within seconds, your consciousness stops. Not sleep, not dreaming. Gone. Hours pass. The surgery completes, the gas stops flowing, and you wake up. No memory. No sense of time passing, as if you blinked. Here's what we don't know. Why does this work? We know anesthetic gases reach your brain. We know they interact with neurons. We can even pinpoint some molecular targets. But we can't explain why breathing in a simple molecule makes consciousness disappear and reappear. How does a gas molecule erase subjective experience? What is consciousness that it can be turned off like a switch? Where does it go? One possibility, controversial, testable, and deeply strange. Anesthetic gases collapse quantum superpositions inside your neurons, which would mean your thoughts, right now, aren't just electrical and chemical, they're quantum. For 30 years, most neuroscientists dismissed this idea as pseudoscience. But in 2024, new experiments are detecting quantum effects in brain tissue. And if they're right, everything we think we know about consciousness, free will, and the nature of mind needs revision. This is the story of the most radical idea in neuroscience, and the experiments that might prove it true. Neuroscience has made extraordinary progress. We understand how sensory information reaches the brain, how neurons encode and process signals, how memories form, how motor commands coordinate movement. We can watch the brain in action, map neural correlates of attention, emotion, decision-making. These are the easy problems of consciousness. Easy not because they're solved, but because we know how to approach them. Measure neural activity, find correlations, build models. But there's a problem these methods can't touch. The hard problem: why does anything feel like anything? You see the color red. Neurons fire in your visual cortex. We can measure those signals. But why does red look red? Why is there subjective experience at all? Philosopher David Chalmers posed it this way. Could there be a being physically identical to you, same neurons, same activity patterns, but with no inner experience? A philosophical zombie? If yes, then consciousness isn't explained by physical processes alone. Something else is happening. This is the explanatory gap, the mystery at the heart of neuroscience. Why does the brain produce consciousness? How do objective physical processes create subjective experience? We don't know. And there's another puzzle, the binding problem. When you see a red apple, different brain regions process color, shape, location, motion. These processes happen in different places at different times, yet you experience one unified perception. One apple, one moment. How does the brain bind these separate processes into a unified consciousness? Nobody knows. Classical neuroscience offers correlations. Brain region X activates when you perceive Y. But correlation isn't explanation. The standard view? Consciousness emerges from neural computation. Neurons fire action potentials, electrical spikes. These spikes propagate through networks. Synapses strengthen or weaken. Patterns of activity encode information. And from this computation, somehow, consciousness emerges. It's called neural correlates of consciousness. The patterns of activity that correlate with conscious experience. Theories like global workspace theory propose that consciousness arises when information is broadcast widely across the brain. Information integration theory suggests consciousness correlates with how much integrated information a system processes. But these theories don't solve the hard problem. They describe what happens when we're conscious, not why it feels like something. Consider: a computer processes information, integrates it, has complex network dynamics. Is a computer conscious? If not, why not? What's the difference? Or consider split-brain patients, people whose corpus callosum is severed. Their brain hemispheres operate independently. Each hemisphere processes information, makes decisions, has preferences. Are there two consciousnesses? One? Neither? Classical theories struggle with these questions. And there's a deeper issue. Consciousness is subjective. Science is objective. How do you measure subjective experience? You can measure neural correlates, but you can't measure the experience itself. You can only ask someone to report it. This creates a methodological gap. Science studies third-person observables. Consciousness is first-person and private. Maybe consciousness isn't reducible to neural activity. Maybe something else is involved. Before we go further, quantum mechanics in biology isn't speculation. It's established science. Photosynthesis, the process plants use to convert light to energy, uses quantum coherence. Light harvesting complexes create quantum superpositions. Energy explores multiple pathways simultaneously. The most efficient path is taken. This isn't metaphor, it's measured. Quantum effects at room temperature in wet, noisy biological systems. Bird navigation. Some birds sense Earth's magnetic field using quantum entanglement in cryptochrome proteins. Enzyme catalysis. Quantum tunneling, particles passing through barriers they classically couldn't, speeds up biochemical reactions. Even DNA mutations may involve quantum tunneling of protons. Quantum mechanics isn't separate from biology. It's part of how life works. So the question becomes, could the brain use quantum mechanics not just for chemistry, but for consciousness? Could there be quantum processes in neurons? Processes that aren't just side effects, but functional? Processes that create or enable subjective experience? Two researchers think the answer is yes. Roger Penrose, physicist, Nobel laureate, mathematician. Stuart Hameroff, anesthesiologist, neuroscientist. Since the 1990s, they've proposed a theory: Orchestrated Objective Reduction, Orch OR. Consciousness, they argue, is quantum. Roger Penrose approached consciousness through mathematics. In the 1990s, he argued that human mathematical understanding involves non-computable insights, things no algorithm could produce. For example, Gödel's incompleteness theorem shows there are true mathematical statements that can't be proven within a formal system. Yet humans recognize these truths. How? Penrose proposed: human consciousness uses non-computable physics, and the only known non-computable process in physics is quantum wave function collapse. Not the standard interpretation, Copenhagen. Collapse happens when an observer measures. But objective collapse. The wave function collapses on its own, driven by gravity at a certain threshold. Penrose's idea. Quantum superpositions create separations in space-time geometry, different configurations of mass energy in different branches. When the separation reaches a threshold, space-time becomes unstable. The superposition collapses. Objectively, without an observer. This is objective reduction, OR, collapse driven by quantum gravity. Penrose calculated, for systems at the biological scale, this might happen on timescales of milliseconds, fast enough to be relevant to neural processes. But where in the brain would quantum superpositions exist long enough to matter? Stuart Hameroff, an anesthesiologist, proposed an answer. Microtubules. Microtubules are protein structures inside cells, part of the cytoskeleton. They maintain cell shape, transport materials, facilitate cell division. Each microtubule is made of tubulin proteins arranged in a lattice. Hameroff proposed, tubulin proteins can exist in quantum superpositions. These superpositions could couple together, orchestrated coherence across the microtubule lattice. And when the superposition reaches Penrose's threshold, it collapses. Objective reduction. Orchestrated objective reduction. Orch OR. Each collapse equals a moment of consciousness. Here's the proposed mechanism. Microtubules inside neurons create quantum superpositions, coherent quantum states among tubulin proteins. These superpositions allow quantum computation, information processing beyond classical limits, exploring multiple possibilities simultaneously. This orchestrated coherence couples across neurons, potentially brain-wide, creating a unified quantum state. When the superposition reaches Penrose's threshold, approximately 25 milliseconds for brain-scale systems, it collapses. That collapse is a moment of conscious experience. A quantum event producing a classical outcome, a choice, a perception, a thought. And this explains anesthesia. Anesthetic gases, sevoflurane, isoflurane, are hydrophobic molecules. They bind to hydrophobic pockets in proteins. Hameroff proposes they bind to tubulin proteins in microtubules. This binding disrupts quantum coherence, prevents superpositions from forming or persisting. No quantum coherence equals no orchestrated quantum state, equals no conscious experience. Consciousness turns off. Surgery happens. Anesthetic clears. Coherence returns. Consciousness returns. This isn't just correlative, it's mechanistic. It explains why consciousness disappears. Orch OR makes testable predictions. 1. Quantum coherence in microtubules should be detectable in brain tissue. 2. Anesthetic binding disrupts coherence. Measurable effect on quantum states. 3. Timescales match. Quantum collapse timescales, approximately 25 milliseconds, should correlate with conscious perception timescales. 4. Ultrasound effects. High-frequency ultrasound, which affects microtubules, should modulate consciousness. For decades, these predictions seemed untestable. The brain is warm, wet, noisy. Quantum coherence shouldn't survive. But that's changing. 2022 to 2024. Multiple studies detect quantum effects in microtubules. Jack Tuszynski's lab at the University of Alberta. Quantum optical measurements show tubulin proteins exhibit quantum coherence at physiological temperatures. Coherence times, picoseconds to nanoseconds. Short, but potentially enough if many tubulins couple together. Anirban Bandyopadhyay's lab in Japan. Electrical conductance measurements suggest microtubules act as quantum resonators. Not proof of consciousness, but proof that quantum effects can persist in biological systems at brain-relevant scales and temperatures. The too warm and wet objection is weakening. 2023. Studies examine how anesthetics affect microtubules. Research shows anesthetic gases bind specifically to tubulin proteins, exactly where Orch OR predicts. And binding correlates with reduced quantum coherence in microtubule preparations. Not conclusive, but consistent with the theory. Meanwhile, clinical anesthesia studies find mysteries. The Meyer-Overton rule. Anesthetic potency correlates with lipid solubility. But there are exceptions. Some lipid-soluble molecules don't cause anesthesia. Why? Classical models struggle to explain this. Orch OR offers a framework. Only molecules that specifically disrupt microtubule coherence cause anesthesia. 2024. Ultrasound experiments show unexpected effects. Low-intensity transcranial ultrasound, used for brain stimulation, affects consciousness in precise ways. Patients report altered states, changes in perception, modulation of anesthesia depth. Why? Ultrasound at certain frequencies resonates with microtubules. Could disrupt quantum coherence. Preliminary. But if ultrasound can modulate consciousness by affecting microtubules, that's consistent with Orch OR. But most neuroscientists remain skeptical. Objection 1. Decoherence. Quantum states decohere too quickly in warm, wet environments. Brain tissue is full of thermal noise. Response. Recent studies show quantum coherence can persist longer than expected. Biological systems may protect quantum states through structured environments. Objection 2. No need for quantum. Classical neural networks can explain cognition, learning, behavior. Response. They explain function, but not phenomenal consciousness, the hard problem. Objection 3. Extraordinary claims. Quantum consciousness requires extraordinary evidence. Response. Agreed. Which is why we need experiments. And those experiments are now being designed. Experiment 1. Detect quantum coherence in living brain tissue. Researchers are using quantum sensors, NV centers in diamond, to measure magnetic fields from microtubules in brain slices. If microtubules exhibit quantum signatures, entanglement, coherence, superposition, at room temperature in functioning neural tissue, that's evidence. Not proof of consciousness, but proof that quantum processes are happening in the brain. Experiment 2. Show that anesthetics disrupt quantum coherence in microtubules. Expose brain tissue to anesthetic gases. Measure quantum coherence before and after. If anesthetics specifically reduce coherence, and if that reduction correlates with anesthetic potency, that supports Orch OR. Preliminary results? Promising, but need replication and controls. Experiment 3. Modulate consciousness with ultrasound. Apply specific ultrasound frequencies predicted to affect microtubules. Measure changes in conscious state. If certain frequencies enhance or suppress consciousness, and if these correlate with microtubule resonances, that's testable evidence. 2025 to 2026. Clinical trials are planned. If consciousness is quantum, what changes? Free will. Quantum collapse is fundamentally probabilistic, not determined, not random, something else. If conscious choices involve quantum processes, they might be neither determined by prior causes nor random chance. A third option. Conscious agency tied to objective collapse, not reducible to prior physical states. This doesn't prove libertarian free will, but it changes the terms of the debate. Mind-body relationship. If consciousness involves non-computable quantum processes, then consciousness isn't just an emergent property of computation. It might be fundamental, tied to the structure of physics itself, not just biology. Death and identity. If consciousness is quantum coherence across microtubules, what happens when the brain dies? Coherence collapses. Quantum states decohere. No afterlife in the traditional sense, but no classical reduction to atoms either. Consciousness might be a process that requires specific physical conditions to occur. Scientifically, quantum consciousness would require rethinking AI. If consciousness requires quantum processes, classical computers, no matter how sophisticated, might never be conscious. But quantum computers might. If they can instantiate orchestrated quantum coherence at the right scale and timescale. Medicine. Understanding consciousness as quantum would revolutionize anesthesiology, psychiatry, neurology. Treatments targeting quantum coherence. Ultrasound therapies. Quantum-based brain-computer interfaces. Physics. If consciousness involves objective collapse, that's new physics. Not currently in quantum mechanics textbooks. It would bridge quantum mechanics and general relativity, the holy grail of physics. But what if it's wrong? Then consciousness remains a mystery, but not a quantum one. Classical explanations might eventually succeed. Computational theories might explain the hard problem after all. Or we might need different, new physics. Not quantum, but something else. The risk isn't in testing the theory. It's in assuming it's true before the evidence is in. Science requires skepticism. Extraordinary claims need extraordinary evidence. Orch OR is a bold hypothesis, worth testing, but not yet proven. Where does Orch OR stand in 2025? Status: controversial but testable, no longer dismissed outright. Evidence: quantum effects in microtubules detected. Anesthetic binding confirmed. Ultrasound effects observed. Gaps: no direct evidence linking these quantum effects to consciousness. Correlations, not causation, yet. Next steps: 2025 to 2026, clinical ultrasound trials. 2026 to 2027, direct quantum coherence measurements in living brain tissue. 2027 to 2028, anesthetic disruption studies with consciousness assessments. By 2030, we might have an answer. But regardless of whether Orch OR is right, it's asking the right question. Is consciousness explainable by classical physics alone? Or does it require something more? For centuries, science has reduced complexity to simplicity. Life to chemistry, chemistry to physics, physics to mathematics. But consciousness resists reduction. It's the one phenomenon where the subjective and objective meet. If it turns out consciousness is quantum, that's profound. It means the universe itself has room for something non-computable, non-deterministic, fundamentally mysterious at its core. And maybe that's fitting. Because quantum mechanics already tells us the universe is observer-dependent. Measurement collapses possibility into actuality. Perhaps consciousness is that measurement. The universe observing itself. Right now, you're reading this. Conscious, aware. Neurons are firing. Chemical signals propagating. Classical processes, certainly. But might there also be quantum processes? Superpositions in your microtubules. Orchestrated coherence creating your unified experience. Objective collapse occurring 40 times per second, each one a moment of conscious now. We don't know, not yet. But the fact that we're testing it, that the question is scientifically approachable, is itself extraordinary. Consciousness might be quantum, or it might not. Either way, we're closer than ever to understanding the greatest mystery. Why anything feels like anything at all. For thousands of years, consciousness was philosophy, religion, metaphysics. Then neuroscience made it empirical. We could study the brain, map neural correlates, understand mechanisms. But the hard problem remained, the explanatory gap. Why subjective experience at all? Orch OR offers a testable answer, because physics itself allows for it. Quantum mechanics creates space for consciousness to be fundamental, not emergent. Maybe it's right, maybe it's wrong, but the attempt matters. If your thoughts are quantum, then you are not fully reducible to atoms and fields. There's something about you, your subjective experience, your consciousness, that involves physics at its most fundamental and strange. Quantum superposition, objective collapse, non-computable processes, the universe experiencing itself through you. Or maybe not. Maybe consciousness is classical after all, explainable by neurons and computation. We'll know soon. The experiments are running, the measurements are being made. And whether your thoughts are quantum or classical, the fact that you can ask the question, that you're conscious enough to wonder about consciousness, remains the deepest mystery of all. This is Cosmic Canvas, where we explore the biggest questions. Until next time, stay curious, stay skeptical, and pay attention to your thoughts. They might be more interesting than you think.